Today we are going to understand how modern AI systems actually work, not just models, but the full system behind. As you can see in this notebook, we are not focusing on isolated algorithms. Instead, we are looking at agentic AI systems, where multiple components, computation, memory, and coordination work together. Let's start with the core idea. At the heart of any AI system is computation. Every model, every decision, every inference is fundamentally a sequence of operation. But computation alone is not enough. What really matters is how efficiently that computation happens. Now, if you look at the sections here, you will notice a recurring theme: computation versus memory. This is one of the most important trade offs in system design. You can either recompute things again and again, which increases compute cost, or store intermediate results, which increases memory usage. So, good systems strike a balance, and this is where algorithms come in. Algorithms are not just abstract concepts, they directly determine how much computation you perform, how much memory you consume, and ultimately how fast your system responds. Now, as you move further in the notebook, you will see how this connects to real systems. When we scale AI systems, new challenges appear. Data movement becomes expensive, memory bandwidth becomes a bottleneck, and coordination across components becomes complex. So even if your algorithm is theoretically efficient, the system can still be slow if these factors are not handled properly. That is why modern AI systems are not just about models, they are about orchestrating computation efficiently across resources. Notice how the notebooks also modular hints at modular design. So agentic systems are built as composable units. One part handles reasoning, another part handles memory, another handles execution. This modularity allows systems to scale and adapt. But again, underneath all of this, the same principle holds. Efficient algorithms reduce unnecessary work. Poor algorithm choices amplify system bottlenecks. So the key takeaway from this notebook is this: high performance AI systems are not built by algorithms alone, and not by infrastructure alone, but by the interaction between computation, memory, and system design. As you go through the rest of this material, keep asking, where is the computation happening? Where is the memory being used? And what is the cost of each decision? Because that is what ultimately defines your system performance. And that is exactly what we are going to build on in the next sessions. Now let's move from concepts into actual implementation, because this is where your as AI agentic systems becomes real. So in this notebook, the first implementation shows a very important pattern: a multi-agent system with a central orchestrator. If you look at the part of this code, we define an agent class. Each agent has short-term and long-term memory. Short-term memory holds intermediate results, while long-term memory persists important outcomes. This mirrors how relay systems manage working memory versus storage. Now notice the process task function. This is where computation happens. Each agent processes a task, simulates some work, and stores the result. But the key idea is not the computation itself, it's how tasks are managed. If you scroll down, you will see a orchestrator. This is the core of the system. So the orchestrator maintains a task queue and multiple agents pull tasks from the queue. Then we use threads to run agents in parallel. This is simple but powerful idea. Instead of processing tasks sequentially, we distribute them across agents. This is your first exposure to parallel execution and coordination. Each agent picks a task, processes it, stores results, and moves data from short-term to long-term memory. This pattern is exactly how large systems work, just at a much bigger scale. Now let's move to the second implementation, which introduces a more advanced concept. Here, instead of just processing tasks, agents now follow a life cycle: plan, execute, and recover. If you look at the thing that is here, you will see these three methods: plan, execute, and recover. This models real AI systems much more closely. An agent doesn't just execute blindly. It first decides what to do, then performs the action, and if something fails, it recovers. Now look at the system orchestrator. Instead of shared queue, we now assign tasks directly and run them using threads again. But the important addition is failure handling. Inside run task, we wrap execution and try except block. If something goes wrong, the agent triggers recovery. This is critical because these systems are not perfect. They must handle errors gracefully. So if you step back and connect both implementation, you will see the progression. First, we learn task distribution, parallel execution, memory management. Then you move to agent lifecycle, planning and execution, fault tolerance. And this brings us back to the core idea of this notebook. AI systems are not just about models, they're about coordinating computation, managing memory, and handling real world constraints like failure and latency. As you move forward, keep this in mind. The difference between a simple script and real system is not the algorithm alone, it's how multiple components work together reliably at scale.